we're going to take a look at something called Demoivre's theorem, which is a very quick way of exponentiating complex numbers, and later we're going to see that we can even take roots of complex numbers. Assuming we had a single solitary complex number of z equal to r cis theta, and we exponentiate that. Writing the cosines and I signs out in full. But we see that the real parts are going to be cos squared and minus sine squared. And the imaginary parts are going to be I sine cos, I sine cos, and cos I sine. So we're going to get 2 sine theta cos theta. Now, what are these things? This is the cosine double angle formula, and this is the sine double angle formula. Well, inclusive of the 2, this is going to be the sine double angle formula. This leads us to a hypothesis that if z equal to r cis theta, that z to the power n is equal to r to the power n cis n theta, where n is a positive integer, and for some reason, instead of powering up the entire cosine I sine, we can actually put the n inside the argument. Let's prove this statement by induction. For n equal to 1, and this holds because base case holds. For our inductive hypothesis, we're going to assume that Demoivre's theorem holds true for some general integer n equal to k, where n is a very final number and k is just some number which is less than n. When I say numbers, I mean positive integers in this case. So our inductive hypothesis can be written mathematically as and this is our inductive hypothesis. Using the inductive hypothesis to prove Demoivre's theorem, we need to prove for the next possible integer where n equal to k plus 1. In this case, we're going to use the inductive hypothesis to prove Demoivre's theorem. Our inductive hypothesis states that z to the power of k for some integer where k is less than n can be expressed as r to the power of k times cosine I sine to the power of k, which is equal to r to the power of k times cosine k theta plus I sine k theta. Now for induction, we will prove for n equal to k plus 1. But what is z to the power of k and what is z? That was z to the power of k. Factoring out the r's. and applying the inductive hypothesis to this term. Expanding all the reals and imaginaries out, but what is this thing here? This is once again the real part is once again the cosine double angle addition, the cosine addition formula. And applying the cosine double angle, the cosine addition formula, and factoring out the thetas. Applying the sine double angle addition formula and factoring out the thetas. So, it seems to hold. So by the principle of mathematical induction, we have shown that Demo's theorem holds true for all positive integers. Let's see how Demo's theorem can be used to power up a complex number currently expressed in Cartesian form. We firstly need to express this in the trigonometric form. So the radius would be and the angle this complex number makes with the positive real axis is going to be so this complex number can be equivalently written in its trigonometric counterpart as, but it's all raised to the power of 4. According to the Demo's theorem, we can simply put the exponent 4 with the coefficient of 4, and we can put the exponent of 4 into the argument of the cosine I sine parts. However, we're not done because the argument of a complex number must always be in the principal domain, where the angle must always be between pi minus pi open and pi closed. We call this the principal domain. And how do we get back into this principal domain? Whenever we get argument which is outside the principal domain of minus pi to pi, we just add and subtract multiples of 2 pi. In this case, we're going to go 4 pi on 3 minus 2 pi to become minus 2 pi on 3. Because Demo's theorem can be used to exponentiate complex numbers rather easily, it can also be used to root complex numbers very easily. If, for some reason, we had a complex number z cubed is equal to 4 root 3 plus 4i, and we wanted to find the 3 cube roots. Remember, if a polynomial has degree 3, we're going to expect 3 roots. But because all the coefficients are not real, the complex roots will not occur in conjugate pairs. So what we do here is that, again, we find the radius of this complex number and we find the cosine I sine equivalent. So this complex number z cubed equal to 4 root 3 plus 4i can be equivalently expressed as 8 cis pi on 6. How will we use Demoivre's theorem to actually cube root this entire thing though? What we would do is firstly realize that complex numbers are periodic, in the sense that because cosine and I sine are themselves periodic and that a complex number is made up of cosines and I sines, the complex number is itself periodic. Let's, for the moment, say that we have a complex number which lies here. If we were to plus 2 pi radians, it's going to get back here. Going to get 2 pi radians again, it's going to get back here. Or even if we subtract 2 pi radians, it's going to get back here. So that's why we need the principal argument of minus pi to pi, so that we restrict our range of complex numbers to be between that special interval of minus pi to pi. That being said, let's actually cube root this. So what we would do is z is going to be, z cubed can still be expressed as 8 cosine I sine pi on 6, but because you just saw that it can rotate an indefinite number of times but still be the same complex number, we need to account for that. Where this counter k is k equal to 0, 1, 2, and so on. K is represent a number of rotations around the Argand diagram. If we were to actually cube root both sides, if we were to bring this 1/3 into the argument of the cis, pi on 6 times 1/3 is going to be pi on 18. 2 pi k times 1/3 is going to be 2 pi k all over 3. Where k equal to 0, 1, 2, and so on. But because this is a third degree polynomial, we will only expect 3 roots, ranging from k equal to 0, 1, and 2. K equal to 0, 1, and 2. And so what are the actual roots? The first root, omega 0, is going to be 8 to the power 1/3, which is going to be 2. We will simplify it later. And omega 1 is going to be what we have here for omega 0 is one solution. Because 13.18 is 1 on 18 plus 2 on 3. And we're still in the principal domain, so we're fine. But we're no longer in the principal domain, so we need to add and subtract multiples of 2 pi. In this case, we're going to subtract 2 pi from 25 and 18 to become and there you have it, the 3 roots omega 0, omega 1, omega 2.